My name is Thomas Graf. I'm probably like the best description would be a long-time kernel developer. A bit more recent, also co-founded a company called iSurveillance, and I created Cilium together with a team. This is not going to be a pure talk about Cilium. I'm going to talk more broadly about rethinking the Linux kernel and why that is happening. Before we get to that, who remembers this age? Nice. Lots of people remember this, right? This is how the web used to look like. Like pre-year 2000, most websites looked similar to this one. How did we get from websites looking like on the left to the age we're used to today, which is what you're seeing on the right, where we spent the majority of our time in a web browser, right? We went from simple web pages showing nice GIFs or GIFs, however you want to pronounce it, to massive applications running in web browsers. What enabled this evolution in roughly 20 years? We went from pretty much markup only, and I'm using like the HTML 2.0 request for comments here, to a age where we use primarily programmable platforms. I'm a kernel developer, so I'm not actually familiar with all of these JavaScript frameworks, but there are a ton out there, and it's basically what allowed this to happen. Obviously, there's a lot more to it, but fundamentally, it is the programmability that enabled to go from pretty much static websites to applications running in web browsers. Why does that matter, and why does that matter for the Linux kernel? We'll get to that. Before we look at a couple of programmability essentials, what does it mean to create a programmable system like JavaScript enables a web browser? First of all, we need some notion of safety, right? If you allow untrusted code to run in a web browser, that needs to be isolated, needs to be sandboxed in some way, needs to be secure. We need continuous delivery, right? There's no point if we extend our application, if we innovate, to then require the user to install a new web browser. Like nobody would ever use any application, any web-based application, if you had to install a new web browser. There was this age where you had to upgrade to new versions of web browsers, and it was very, very confusing to users. We're no longer used to this. We're used to pretty much automatically getting updates for both websites and browsers on the fly. Probably you don't even notice when you upgrade your Chrome at this point. And you definitely don't notice unless there is some visual appeal or some visual change that a website has changed its backend, for example. This is all happening continuously and seamless, right? If you deploy a new version of your app, you will have potentially millions of users on that website at that time. You want to seamlessly upgrade. So any programmable system needs to have some notion of continuous delivery and seamless upgrades. And the last aspect is performance. If we gain programmability and we sacrifice performance, the programmability is probably not worth it. A good example of this is the early stages or early years of Java, where there was a huge performance penalty. A lot of that went away later on, but initially the cost of running Java, or the difference running a C++ application and a Java application, was huge. Similar with JavaScript. Like before JIT compilers, running JavaScript added a considerable amount of CPU usage on users' laptop or on users' end machines. So any sort of programmability aspect also needs the notion of native executions. And in a lot of instances, this is being done with just-in-time compilers or JIT compilers, where some notion of generic bytecode is being translated into what the CPU that your machine is running actually understands. So we're getting to as close as possible to native execution speed. So the second aspect, before we can connect the two pieces together, is to do a super quick, not a deep dive, but a super quick introduction to kernel. How does the Linux kernel look like? And roughly there are three pieces. We have a user space. That's like kernel people like to put that on top. And then below that is the Linux kernel, the operating system, and then on the very bottom layer is the hardware. Then we have some notion of process. This could be an application, some task running in user space, and on the bottom layer we have hardware. And I've massively simplified this storage network. Obviously there's many more pieces of hardware, but I've simplified this as much as possible. Then the first thing the kernel will do is it will abstract this away using so-called drivers. So the kernel obviously needs to understand the hardware and needs to enable it, but it doesn't want to expose this complexity straight to the applications. So it will introduce the first level of abstractions. So the Linux kernel will understand, I'm aware of block devices, I'm aware of network devices, I'm aware of like an input-output device, I'm aware of a console, and so on. It's the first level of abstraction. Similar, we have so-called system calls, which is what an application invokes to communicate with the Linux kernel. There's many of them. I've used a couple of examples here. One to do file I/O, a read and write. This would allow to read files, write to files, and also send message and receive messages. This is what an application would use to network interaction, to actually send data on a BSD socket or on a TCP socket. This is what the kernel exposes to the user space and to applications. This is where the kernel provides guarantees in terms of backwards compatibility. This is the API that does not change, allowing for applications to continue running even if the kernel actually evolves. And then we have middle layers, middleware in the middle. This is where the logic is. This is kind of the business logic, like the virtual file system, process scheduler, networking, TCP/IP, firewalling technology, and so on. All of this is in the middle. And then the last piece is somebody is actually operating this system. In the past, this used to be an actual human being. These days, all of this is pretty much automated. And this is being done through configuration APIs. And over the years, the kernel has taken on many different APIs. We have systemfs or sysfs, procfs, netlink. There are many more different APIs, how either a human or a controller or some script or some component can interact with the Linux kernel and configure these systems. For example, mount the file system, change the firewall rule, load a new driver, load the Linux kernel module. All of these things are done through these APIs. So that was like a super quick 101 into Linux architecture. Raise your hand if you want more details here. I see a couple of hands. So we'll go into the kernel development process. So like, what do you do if you want to change any aspect of that? So like, what options do I have if the Linux kernel as it stands right now does not provide what I need? You pretty much have two options. You can either go ahead and do a native implementation, or you can write a kernel module, and we'll look at both. So native support, it means changing kernel source code. It means going upstream to the Linux kernel mailing list and convincing the world that this change is really needed. And whatever complexity you're adding, the rest of the world should be paying. It means exposing in some sort of configuration API to actually expose that and to actually enable it. And then you have to wait 5 years until all your users actually upgrade to the latest Linux kernel version. So this is nice once it is in, and once these 5 years have passed, the whole world will basically have this capability. The problem with that, we don't really have time for that. Right? Like nobody wants to wait these 5 years. The second aspect is a Linux kernel module, which is a loadable plugin that you can load into the Linux kernel at runtime. It will extend the kernel functionality. It's basically like a shared library that you can load. The problem with that is the kernel does not have any stable APIs inside. Like only the user space facing pieces are actually stable, which means if you write a Linux kernel module, it will break with probably every single kernel release. So you will basically but adjust the source code of your Linux kernel module with every Linux release as it goes along. And you probably have to ship a different kernel module for all the different Linux kernel versions. And the most horrible part is if you have any bug in that Linux kernel module, it will just bluntly crash your kernel. So probably you want to be very careful before you ship a Linux kernel module to any of your users, because you might literally just kill the machine. So these are not really great options. So we've talked about JavaScript and how that helped evolve web browser applications to become huge and basically take over the world. We looked into Linux kernel and like the options we have to extend it, and that they're not really good options. How can we combine the two? Well, how about we add something like a JavaScript-like functionality to the Linux kernel? That sounds appealing, right? It should solve all the problems we have. So this is basically eBPF. It's like almost literally eBPF. And we'll take a deep dive into what that actually does. So first of all, if you go back to our description, what a user space application or a process does when it interacts with the operating system, it performs system calls, right? For example, the exec system call is used to launch a new process. So if you type something in your bash, in your shell, and you run a new command, the bash shell will run an exec VE system call to launch a new process, to launch, for example, top or PS or whatever binary you're running. And then the scheduler will basically fork the process and so on, right? What eBPF allows us to do is something that's pretty amazing. It allows us to take that system call and run a program that takes over on behalf of the system call and then returns. So we can do something like this. We can define a BPF program that will execute on the return of the system call execVE, and it will execute this code. This example code will basically extract some metadata from the system call, such as the binary name or the com name, and send that through a BPF map, and we'll get to that, and expose that to user space, for example, for audit or tracing purposes. This is how BPF-based tracing works, where we can trace all the system calls that are being done and provide context along with that. So this is one example how BPF allows us to run almost arbitrary code at various hook points. This example is using a system call. We'll look into all the other hooks we have as well. How does that work exactly? Like, how do we actually execute code in the Linux kernel? How do we define that program? How do we load it in? There's a so-called BPF runtime. And the runtime will also ensure that we guarantee and fulfill all of the programmability requirements or the programmability essentials that we covered earlier. So there's some program, BPF bytecode, which is basically the compiled version of the code that we have seen in the last slide. And you as a user, you want to load this and actually run this as part of a system call. You will call the BPF system call and load this program. Say, I want to load this program whenever this system call is being invoked. The kernel will then take this program and will pass it through the BPF verifier. The verifier will ensure that the program is actually safe to run. So this is the first major difference to a Linux kernel module. If the BPF program is buggy or it has some flaw, it cannot crash the kernel. The verifier will ensure that the program is safe to run. If it is not safe to run, it will reject it and you cannot load the program. It will, for example, also ensure that you have privileges required to actually load the BPF program. It will, for example, assure that you cannot access arbitrary kernel memory. It will assure that you cannot expose arbitrary kernel memory to user space, and so on. It guarantees that a BPF program is safe to run. And only if that passes, the program can be attached. So very, very similar to JavaScript, where exactly the same is being done as well. There's also a software-based runtime or a software-based sandbox, which ensures that a JavaScript program running as part of one tab in your Chrome browser cannot basically access the entire memory of all of your Chrome tabs, for example. The next piece is once this BPF program is passed, it is approved, and it will go to the JIT compiler, the just-in-time compiler, where the generic bytecode, which is entirely portable, so you can load this bytecode on x86, on ARM, whatever CPU you're running. The JIT compiler will take this and compile this to the native CPU that your system runs. For example, x86, which means instead of interpreting bytecode in software, we are now executing a program that runs at the same speed as if we had compiled it natively and loaded that in. So now we are almost at a point where we have a kernel module, but it's done in a safe way. We cannot crash the kernel, right? And then after it has passed through the JIT compiler, we can attach it to the system call. And this is where, or like various other hook points that we'll get to. And this is where the last piece is coming into. continuous delivery. We can replace these programs, these BPF programs, in live systems, in Linux kernels, without impacting applications. Right? For example, if we take a network-related program that processes network packets, we can replace that program atomically, which means, let's say we're processing hundreds of thousands of packets per second. Between one and the next packet, that program is atomically replaced. The last programs are, like the last packets are the old version. The next packet will see the new version. There's no breakage in any way. This is allowing us to continuously run systems while upgrading our logic without breaking any, for example, TCP connections or actual applications running, and so on. So we are fulfilling the 3 programmability essentials that we covered earlier. So hooks. I've always been talking about system calls, but also mentioned networking. There's many different hooks where you can connect or attach a BPF program to. If we start from the top, we can attach to arbitrary system calls. So whether it's a TCP file open, a send message, a socket, like creation of a socket, executing a program, all the system calls we can attach to. We can also attach to user space applications. So we can run using so-called U probes or user space probes. We can run a BPF program for particular functions in your applications. This is how you can profile applications using BPF. We can attach to an arbitrary trace point in the Linux kernel. A trace point is a well-known defined function name of the Linux kernel that will stay stable over time. While the kernel functions are changing per release, trace points are valid and they will stay stable. So this is allowing to instrument the entire Linux kernel. We can use fentry, fexit. Like for every kernel function called, at enter and at exit time, we can attach a BPF program. We can attach to various sockets and actual network events. So for example, TCP level. Right? We can implement TCP congestion algorithms using BPF. We can attach at the network device level. So for any virtual or physical device, we can attach a BPF program and it gets invoked for every network device, every network packet that is being received or sent. We can even go and offload this to hardware. So we can attach a BPF program and work together with the NIC to actually offload the program. So as your physical network card receives a packet, then if the NIC is programmable, it can run the BPF program. So we gain programmability and we can attach this logic at a very wide range of different hook points. And when we get to the use cases, you will see how wide the actual examples and how wide the use cases are that can be solved with eBPF. So nice. So we can run programs. What can these programs do? Like one essential piece about any program where the complexity usually comes in is state. Where can we store state, statistic, metrics, and so on? And this is where eBPF maps are coming in. So a BPF program itself is only the instructions. Right? It will not contain actual data. Like there is no memory in the sense of that we can dynamically allocate memory on the fly. Any sort of state that is stored in BPF maps. And it's very important these are separate from the program, which means we can keep the map alive. For example, we can create a map which is implemented as a hash table or as a stack. We can keep this alive while replacing the program. This is, again, allowing the seamless upgrade, right? So let's say we have a program that's actually collecting stats, for example, or metrics. We can replace the program logic without losing that state. Maps can be accessed from the BPF programs itself, so they can be used, for example, to share information or state between different programs, but they can also be accessed from user space. So we can have a user space application or some CLI or like some tool that allows to retrieve or configure aspects via BPF maps. Different types exist. So like on the left, the lower left, you see the different map types. We have hash tables. We have least recently used hash tables. This is allowing us to dynamically size it, which means like the oldest entry or the least recently, like the oldest entry will always be expired if the map becomes full or if we run out of resources. We can use ring buffers. So we can send actual events to user space. We have a stack trace and we have a longest prefix match, which is a specific networking implementation to implement routing tables. So just a subset of all of these map types. There are more map types being added as the use cases are growing for eBPF. Helpers. So a Linux kernel module can pretty much call any kernel function, which has upsides and downsides. The upside is a Linux kernel module can reuse any functionality that is part of the Linux kernel. The downside is if you abuse this or if you misuse it, you will crash your kernel. And the second aspect is obviously the internal list of functions is changing all the time. It's not stable. Right? So if a function is being removed and your kernel module relies on it, the kernel module will no longer compile. And if you load it, it will not load. It will say, like, I cannot resolve a certain symbol name. With BPF programs, this is done differently. They're so-called eBPF helpers, which are used to interact with the operating system. And they are stable. So the subset of helper functions that exist, they are stable over time. And they're being maintained backwards. For example, a BPF program does not know how to generate a random number, but there's a BPF helper that will allow to retrieve and ask the kernel, give me a random number, or give me the current time, or redirect this network packet to this device, or, for example, read a certain value from a BPF map, and so on. Any sort of interaction with the operating system is being done via BPF helpers, and because these are stable APIs, BPF programs are portable across kernel versions. Tail calls and function calls. So instead of composing one big program, we can divide our programs into multiple small pieces and do tail calls and function calls. Function calls are pretty much exactly the same as you would expect from a different programming language. Tail calls are a little bit different. Tail calls are more like an exec, which means you can replace the context of your programs. You can basically chain programs together, but once the program is finished, it will not return to the old program. So it's basically more of a chaining. It allows programs which may not even be aware of each other to be chained together. So you can, at a certain hook, run multiple logical pieces after each other. Tail calls and function calls are used, obviously, to make BPF programs composable. They're also used to reduce the size of the program. Obviously, we could tell the compiler to inline everything. Like even if we use function calls in our source code, we could inline everything, generate one large program, even as part of source code. That would just increase the size. So function calls are primarily used to reduce the size of our BPF programs. Okay, nice. So all of this is great. Who is actually responsible for this? Like who can I bug if something is not working? Who's behind this? It's a huge community. It's been pretty invisible, actually, given how many people have been working on this. And the main reason is because most people involved in this don't really have much of an interest in this becoming widely known. Or there's no interest in marketing. Let's put it this way. Right? There's definitely an interest in sharing the overall cost of maintaining this. But primarily, this has been used by very, very large cloud providers, for example, or other large-scale infrastructure companies, which have very specific needs around the Linux operating system, and they did not see an ability to fulfill their needs by implementing kernel source code changes, but basically switched over to using eBPF to fulfill their needs. So you can see like large companies like Google and Facebook like maintaining this and driving this forward. And then the third big player in there you can see is Cilium. That's us. And we'll get to Cilium, where we have obviously been involved very much in maintaining eBPF as well. Structurally, there are two maintainers. So there's Daniel Borkman and Alexis Daravoita from Facebook. Daniel is working for us, co-maintaining eBPF. eBPF projects. So I've touched on a couple of them. This is giving you, obviously this is just like a very small subset, but this gives you like a glimpse into the width of active users of eBPF. So starting from the upper left, Facebook is massive usage of eBPF. Maybe the most well-known usage is Katran, which is a high-performance load balancer they've done to replace IPVS, which is another software-based load balancing solution that Facebook has been using before that. They've switched over to using eBPF and saw a massive performance increase because of that. And they've open sourced this, so you can go to the GitHub there and check out the code. It's definitely specifically built for the Facebook infrastructure, but if you're using a Linux-based software infrastructure system, you could use this as well. Then obviously we have Cilium, but we'll get to that in a bit more details, providing networking, security, and load balancing for Kubernetes. We have BCC and bpftrace. Many people working on this, but the main person, I'm not sure whether it's fair to say, but the main person behind this is probably Brendan Gregg, working at Netflix. This is applying BPF for profiling and tracing. So gaining understanding of what my application is doing, what is the system doing, figuring out why the application is not behaving in terms of, for example, how many block IO calls is it making, and so on. We have the Android team and Google in general investing heavily into BPF. So for example, there's a BPF loader in Android. There's a network traffic monitor in Android. There is the KRSI, the runtime security infrastructure done by Google, and so on. Then Cloudflare. Cloudflare has many blog posts on how they use eBPF for traffic optimization and QoS. If you're interested in that, I would suggest you to check out these blog posts. They've also open sourced various toolings around BPF. And then there's Falco from Sysdig, a CNCF project, which is applying BPF for container runtime security. So introspecting system calls and then detecting whether certain system calls, certain metadata around system calls could actually indicate that some security-related threat is going on. So that's a glimpse into some of the use cases. We'll dive into some of them. So first of all, there is like BCC. Maybe the most well-known application of BPF at this point. So how does BCC work? So BCC stands for BPF Compiler Collection, I think. And it's allowing application developers to write a Python program which contains both the actual BPF program which will run and generate events and metrics, and then also the logic in Python to read the state, the metrics from the BPF maps and display that in some way. The lower right gives you one example. For example, this is a TCP top PCC program which will attach a BPF program to all send message and receive message system calls and then maintain a list of all TCP connections, I think also UDP connections, or in this case only TCP, and then also record how many bytes are being transmitted, for example. It's using exactly the same kernel subsystems, right? It's going through the JIT compiler, it's going through the verifier. What's specific about BCC is the user space component that is actually controlling this. So the ability to write a Python-based program that will then automatically load the BPF program and so on. If you go to iovisor/BCC, obviously it's open source, there's a huge collection of different programs where you find many pre-cooked small programs that you can use to monitor your systems, like from networking, storage. There's stuff like show me all the files that are being opened. It's hard to mention because so many different examples. Like almost any hook that can somehow be used for tracing and profiling will have an example program in that repo. So you don't have to actually write the BPF programs yourself. You can pretty much reuse a lot of the pre-cooked examples there. So this is in Python. And then there's more recently there has been a project introduced called bpftrace. And it's, to sum it up, it's pretty much DTrace for Linux. And the main difference here is instead of writing Python programs, you can write a program in a new higher level bpftrace syntax. Same scope, same focus. So it's still about profiling and tracing, but you don't need to write Python programs. Otherwise, it works exactly the same. In this case, it's an example on how to use bpftrace to record all file opens. So as we run bpftrace and we specify to attach a program at the kernel probe called doSysOpen, that's an internal kernel function, though that's not the system call, that's the actual kernel. There's a kernel function called doSysOpen, which is the function that's called by the system call. Then like invoke this program logic, like the printf, and just basically invoke the com string and the first argument, which happens to be the file name that is being opened. So this gives you the programmability. It's a single line, but it's a lot of logic that goes into that. And it will automate everything from creating the BPF maps, reading that, and so on. So this is bpftrace, also open source, also in the iovisor org. Then we're going into Cilium. So Cilium is broadly networking, load balancing, and security for Kubernetes. And the main aspect, the main goal of it is to take all the power of eBPF and then bring that to the Kubernetes world and not have the user base actually need to understand BPF. Obviously, it's a very, very low-level technology, right? And yes, it can be used to very, very effectively implement, for example, Kubernetes services. But users, they just want to load a component that will then translate Kubernetes services or the implementation of that and implement it with eBPF. They don't want to necessarily care much more about it. Cilium automates all of that. So, for example, we implement network policies, Kubernetes services, and so on. Cilium uses a wide range of hooks. So we are starting obviously at the network hardware level where we can, for example, do DDoS mitigation. We can do load balancing at the network layer. Then we are at the software network device level. We are using sockets where we actually introspect the data that an application is sending in and out. That's how we can, for example, look into the layer 7 aspect without running a full layer 7 proxy. And we're also looking at the system call level to, for example, do load balancing with the connect system call, and so on. I will not go into all of the details, but we're using the full range of hooks that are available and are abstracting this away nicely so you can basically run Cilium as either a CNI plugin or just a daemon set and configure everything through the standard Kubernetes objects and resources that you're used to, such as services, network policies, and so on. This is the full overview of everything we're doing, like container networking. So we provide very efficient, flexible networking with BPF. We can do, for example, overlays. We can do native routing. We can integrate with cloud provider IPAMs. We can do multi-cluster routing. Obviously, we have v4 and v6 support. We can even do things that the Linux kernel itself cannot do, such as NAT4.6, translation between IPv4 and IPv6. We can do service load balancing. We can completely replace Kubeproxy, so you can get rid of IP tables entirely on your Kubernetes nodes. We can do direct server return, and so on. Container security, another huge focus of Cilium. We are using an identity-based approach, so we're not using IP and port-based firewalling technology, but instead we're allocating security identities to workloads and enforcing based on that. Also something we can do with BPF, which would not be possible with the existing Linux kernel frameworks. We are API aware, so we not only understand network packets, we also understand layer 7 calls such as REST, Memcached, Cassandra, Kafka, gRPC, and so on. We are DNS aware, so you can define security policies instead of whitelisting or specifying network firewall rules based on IP addresses. You can, for example, allow star.mycorp.io, and then all IPs returned by the DNS for that pattern will be allowed by our firewall, so you don't have to, for example, hard code IP addresses. We support transparent encryption. We have SSL data visibility, and so on. So a wide range of use cases that we can implement using BPF. And then very recent, we also open sourced Hubble, which is the visibility component of Cilium. Super exciting. It's basically building on top of the existing eBPF framework that we have in Cilium, then adds a visibility component on top, which provides mainly two things, or three things. A very nice service map, what you can see in the upper right, where you can dynamically, transparently generate an overview of which services are talking to what other services. Got like a service map overview, like what services are actually talking to each other. You can go all the way into layer 7, so you can actually see the HTTP calls being made and so on. Then we have metrics. So all of the visibility that eBPF gives us is being translated into metrics that we serve. And then we also have flow logs. So if you want to record all the network connectivity that went on, you can expose that via flow logs. So this is Hubble, all BPF powered. A lot of this would just simply not be possible without BPF. Like if you would try to implement this based on an IP tables packet counter, that would be incredibly hard to do, for example. So this is a good example of like the programmability aspect giving us this huge leap forward in terms of driving features. What if you wanted to develop, let's say you don't want to use Cilium, you want to do your own Go program, or your own BPF program. How do you do that? How do you write a BPF program? How do you load it? What type of tools are available? We have open sourced the entire tool chain we have, and we use for Cilium. It's in the library in the repo cilium-/eBPF. And it's obviously still using exactly the same Linux kernel components. And it is a library that sits on top, which is what we call the eBPF Go library. And it will hide the abstract away both the system call that will load the programs and create the maps, and also the access of the maps. So all of that is nicely hidden away and exposed as Go types, program and maps. So you can basically load a BPF program by using a Go library, and you can create, read, write from maps and to maps using Go bindings as well. How do you define the actual program? There's many ways of doing this. The one we use most is to write it in a higher level, from a BPF perspective, higher level language such as C code, and then use Clang with the BPF backend target to generate bytecode. So you can write the program similar to like one of the examples we have seen earlier, run Clang, and what you will get is generic BPF bytecode. And you will have your controller program using the Golang binding, which will open that generic bytecode file and will load it into the Linux kernel using the system call. The verifier will actually verify it. The JIT compiler will compile this into your native CPU and then attach it to the system call or to the hook that you define. So from a user perspective or from a developer perspective, you can use Clang plus the Go library to inject arbitrary programs at various hook points. On the actual runtime, so what will run on the system is only the Go library and your controller. Obviously, you don't need to run Clang on the system where you actually load the program and where you attach it. So you can, for example, run Clang on your laptop, generate the bytecode, ship the bytecode, and use the Go library to load it. All right, outlook into the future. So eBPF sounds amazing. Is this all you can do? Like initially, the title was Rethinking the Linux Kernel. So what exactly is the rethinking part? And there's two aspects here which are very interesting. All of what I've just talked about sounds kind of normal and natural, right? It's like, oh yeah, this makes sense. Like, why haven't we done this earlier? All makes sense. But what's kind of happening with this is that we basically, by accident, kind of went the microkernel route. So for those of you who were not super deep into operating systems, a long time back when Linux was first created, there was a huge debate about how should operating systems be designed. And it was, yeah, either you go microkernel, kind of like similar to how microservices are being written today, or you create a huge monolith. And Linux was the best example that the monolith was the better approach, right? Single code base, huge code base, single binary that you run. Linux kernel modules came way later, like much after this debate. The Linux kernel was not really extendable in the very beginning. Huge code base, compile, 5 megabyte binary that you load when your machine comes up. And with BPF, we're kind of quietly, without even noticing maybe, went down back to the old discussion and have started to implement a microkernel model where we can now dynamically load programs. We can dynamically replace logic in a safe way. We can make logic composable. So we're going away from the requirement that every single Linux kernel change requires full consensus across the entire industry or across the entire development community. And instead, you can define your own logic. You can define your own modules and load them safely and with the necessary efficiency. A very good example of this, I think, is Cilium itself. The Linux kernel itself has no clue what a container is. This may be very surprising, but there's no such thing as a container ID in the Linux kernel. The Linux kernel does literally not know what a container is. The Linux kernel knows about namespaces, right? The Linux kernel knows how to do resource management. It knows, oh, I have a C group, and the C group has certain CPU constraints. And these are the processes that are attached to this C group. And it so happens that the container uses C group, or the container runtime uses C group for resource management. the Linux kernel has a concept of network namespace. Oh, I can have multiple virtual network scopes, and each of these scopes can have its own IP address and so on. The kernel does not know that container is using a particular network namespace. In fact, if you are using Kubernetes, a Kubernetes pod will have 2 containers, and both of them will share the same network namespace. So there's not even like a tight coupling between network namespace or namespace and particular container. The kernel does not know about anything at all about containers. It only provides the tooling. And this has been a big problem, right? Because the kernel stopped being able to deliver functionality that is essential, right? Because it was not aware of containers. Cilium is adding this ability to the kernel, making the kernel aware of containers and, for example, Kubernetes services without requiring to change the kernel source code, right? Because the changes that Cilium needs may not be acceptable to the 80% of non-Kubernetes use cases, for example, right? So the kernel community would not be willing for everybody to pay the cost of the complexity that Cilium is adding for the Kubernetes-specific use case. So this is definitely a huge shift, and there was no debate about this. It just naturally happened, and everybody's fine with this, or the majority is fine with it. And then the second aspect, this is a really big outlook into the future. So who's running more than, let's say, 5,000 either servers, VMs, or something like that? All right, how long does it take you to reboot all of them? You don't know? Maybe you have never had the need for it. But if you, let's say you run 5,000, right, and there's some kernel security bug, and you need to reboot all of them, how do you do that without sacrificing or without introducing massive downtime? Like, you need some sort of schedule, right? You can say, oh, I can reboot like 2% of them at a time, and then that may take you, let's say I can reboot, I don't know, 10 per 5 minutes or something. It will take you quite a long time to actually reboot them. Imagine this at scale of like Facebook and Google and others, like hundreds of thousands of servers. It may take weeks to reboot all of that. So some of the systems will be vulnerable to the kernel bug for weeks. And that's not really acceptable. Right? If you have a 0-day bug coming out, you want to protect yourself as quickly as possible. If you're lucky, you can somehow catch like what's actually you can have some firewall rule that may be able to catch it, then you're lucky. But if it needs a hot patch, you will be out of luck, and so your systems, you have the choice, either downtime or like having a massive buffer of machines that are unused, or you just have systems that are unprotected. So the solution to this might be eBPF. I've used the Heartbleed example here, but we could use any type of security bug of like similar scope. Obviously, in these scenarios, like some kernel function or something is vulnerable inside of the Linux kernel, and a hotfix would typically patch that function and change the logic of that. So what if we, instead of changing the Linux kernel and rebooting, what if we could actually do the hot patching on the fly? And this is not completely new, not at all. Like, hot patching has been available for a while, but it has never really been solved well enough that it is spread widely. It's been insecure, difficult to use, and so on. eBPF could be the solution to this, where instead of patching the kernel, we basically bring a BPF program in which runs on behalf of the insecure function and implements the same logic but without the actual bug. Right? Zero-day fixes are only one example. There's only many other bugs that could benefit from a similar treatment. So this is definitely something that has sparked a lot of interest, and there's lots of discussion on how this how eBPF can be used to solve this. All right. With that, I want to say a huge thank you to everybody on the left. I'm not going to read all of the names, but I wanted to give a big shout out to like all like the huge community that has been involved in getting BPF as far as it is today. Starting with like the actual eBPF maintainers working day and night almost, like the Cilium team, Facebook team, Google team, and so on. Like long list. It's a absolutely wonderful technical community. This has been evolving incredibly fast and quick, and it's a joy to work with all of them. If you want to learn more about BPF and XDP, which is the network device BPF program, there's a getting started guide, which first of all gives you like the full language spec and also introduces you how to write BPF programs. There's obviously Cilium that you can look at, which is Kubernetes specific, and then the previous slides with BCC and bpftrace, the links are on the slides itself. If you want to learn more about Cilium and follow us, you can follow us on Twitter, and if you want to reach out to me, you can follow me on Twitter as well. With that, I think we have a couple of more minutes for questions. Excellent.
All right, questions? Everyone's stunned to silence.
Yes. Thank you for the amazing talk. I have a question about the verification process of these. So, what happens if, like, there's one program that is in itself safe, the second one is safe, but in combination they are unsafe? Can that happen, and what will happen then?
It should not be able to happen, and the reason for this is it's not possible to do arbitrary function calls between programs. Like if we do a so-called tail call between programs, then the amount of context that you can put into a program is very limited. By that I mean, so you can't just take the memory from the old program and give that to the new program, for example. You can pass on a very limited amount of well-defined types like numbers, strings, and so on, right? But you can't. So it's well known, and the verifier can validate that all possible combinations of the input to the new program are safe to run. So no matter what state the old program leaves behind before we do the tail call, the verifier guarantees that it is safe to run. So the verifier will test all possible combinations that can happen. Did that answer the question for you?
So thanks for the, hey, here I am. Thanks for the amazing talk, and I would like to ask actually, with the observability features that are built into Cilium, where do you see the line between a service mesh like Istio, which you said that it's compatible or integratable in this tool stack, yep, and Cilium? This is question number one. And question number two, I would like to know whether you said that it can run as a CNI plugin. So, for example, if somebody uses Kubernetes on EKS, and it obviously comes with a AWS CNI plugin bundled in, does that work in any sense? Like, can you still use Cilium, or does it exclude that? Thank you.
Yes. So first question. Obviously, there is some overlap in terms of both projects will provide what's typically referred to as tracing. The biggest difference is that Cilium is 100% transparent. Right? It does not even inject a so-called sidecar proxy. So there's nothing that the application will not even understand or notice that anybody is observing anything. All the observation is done using kernel-level BPF programs. And then we can also transparently inject Envoy as a proxy on demand. But not in a sidecar model where the actual proxy that was providing the visibility runs inside of the application container. It's running outside, hidden away from the application. So the biggest difference is the transparency aspect. And the second aspect is that because of BPF, we can provide this visibility at much better efficiency. So you will have less overhead as you add this observability. Other aspects, for example, the DNS awareness is something that Istio and Envoy do not provide yet. They may in the future. In general, it's not an either-or decision at all. Like we have many users that will run Cilium and, for example, Istio or Linkerd or some other service mesh. It's perfectly fine. What we see very commonly is that this visibility is used by the platform team, the security team as the ground layer for everything, and then different application teams, sometimes even different teams running in the same clusters, will pick different service meshes based on their needs. And this service mesh obviously provides several aspects that Cilium does not provide at all. Cilium does not do any layer 7 load balancing. It does not do any circuit breaking. It does not do any retries. None of that. Like we are focusing on visibility. And also the last aspect in that is we are also providing a lot of operational metrics. So for example, we allow to detect situations where DNS resolution failures, which is a very common cause for outages, that you can notice and observe them earlier, which is something that the service mesh is less focusing on. Your second question was on EKS. Yes, so Cilium has two modes. You can run it in native AWS modes, where we basically provide exactly the same model as the standard EKS CNI provides, so it's fully compatible. It also uses what's called AWS ENI. It's what probably our largest users use. scales to like massive numbers. And then the second deployment model is you can run Cilium in chaining mode, where you can run it on top of, for example, the AWS CNI plugin or on top of the GCP network CNI and so on. So both are viable options. Typically, we recommend to use the native mode for any large deployment.
Thanks as well from my side for the talk. One question which actually ties into your question is, are you open tracing API compliant, or because they kind of try to merge all the tracing efforts, and is it already compatible or is it planned?
It's planned, so we don't output the open tracing spec yet. The main reason for this is that these systems have been built with a slightly different design in mind. Most of these tracing libraries, they're basically built that you're running on behalf of the app and you're reporting on behalf of the app, and we're more kind of a transparent middle system. So we're basically reporting both sides at the same time. This is making it a bit challenging to do this, but we are working on this to implement the open tracing API. Yes.
Hi. You mentioned using Clang to compile the
Yes.
eBPF programs. Does that mean that any language that has an LLVM front end can be used, or is it only C?
I think you can use other languages. So as long as Clang supports high-level to intermediate to BPF backend, you can use any language you want. I'm not enough of a Clang expert to make the claim that any of the languages will work. But as long as Clang supports that translation, like the Go library, all it will expect is BPF bytecode. And how you generate, you can even write that bytecode by hand. GCC also supports BPF backend by now, so there's multiple ways on how to generate that bytecode.
Okay, we're out of time. He'll still be around. The next talk is at 4:10. It'll be the Tesla talk up in the keynote area. Thank you.
Thank you.